Welcome to Algebra, Writing Systems of Equations, Part 1. Now that we have studied several ways to solve systems of equations, let's take a look at why we even do this. When will we use a system of equations in the real world? This is a fair question, and this lesson will look at several situations where writing a system of equations is an appropriate way to solve a real-world problem. Here is a simple scenario involving the price of apples and peaches. We want to find the individual cost of each fruit, given two different purchases. In the first one, the total cost of 3 apples and 2 peaches is $3. The second purchase buys 4 apples and 1 peach for $2.75. From these two transactions, we want to find the cost of each apple and each peach. To do this, we represent the apple and the peach with the variables x and y, x being apples and y being peaches. This must always be the first step when setting up equations to represent a real-world situation. Identify what the variables mean and write it down. This way, when you finally reach a solution, you remember what it means. From the problem statement, we express the two purchases with an equation-like sentence for each, and then actually write each equation. 3 apples plus 2 peaches equals $3 becomes the equation 3x plus 2y equals 3. 4 apples plus 1 peach equals $2.75 becomes the equation 4x plus y equals 2.75. Now it is time to solve this system of equations to find the cost of each fruit. Consider all the different ways you have learned how to solve systems. Graphing from slope-intercept form, substitution, elimination, and choose the one you think would be the best approach. Since both these equations are in standard form, it would make sense to use elimination, but the others work as well. Let's see how elimination works. First, we see that the y term coefficients 2 and 1 relate very easily, and so multiplying the second equation by -2 will cause the y terms to be eliminated when the equations are combined. We end up with -5x equals -2.50, and then solve for x to get 0.50. We then substitute this value for x in the first equation, solve for y to get 0.75. Graphing these two equations in Desmos confirms this solution, 0.5 for x, 0.75 for y, and applying these values to the original variable definitions expresses the cost of each fruit, 50 cents for an apple and 75 cents for a peach. Problem solved. In this situation, a bus travels two different routes, the green route and the blue route, each one a different length. On Monday, the bus traveled the green route 6 times and the blue route 5 times, for a total of 52 miles. On Tuesday, the bus traveled the green route 12 times and the blue route 13 times, for a total of 119 miles. The question is asking about the length of the green route. To do this, we need to find both, and so we set up two variables, x and y, to represent these two routes, x being the length of the green route, and y the length of blue. The equation-like sentences would be 6 times green plus 5 times blue equals 52 miles, with the equation being 6x plus 5y equals 52. And the second sentence and equation being 12 times green plus 13 times blue equals 119 miles, and then 12x plus 13y equals 119. Elimination also works well for this standard form equation system, since the x coefficients 6 and 12 easily relate. We multiply the first equation by -2, causing the x terms to drop out when they are combined. Solving for y finds 5 as the solution, meaning the blue route is 5 miles long. Substituting this value in for y and solving for x finds the value 4.5, the length of the green route, which is confirmed by the Desmos graph and is choice G in the original equation. Here is a classic money counting problem that is easily solvable using a system of equations. It describes a collection of 18 quarters and dimes totaling $2.85 and asks which set of equations would represent the correct system to solve this problem. The examples use the variables Q for quarters and D for dimes, which certainly makes sense. The key is to express the quarters and dimes with their corresponding values of 0.25 and 0.10. The first idea expresses the total value of the coins by adding the value of the quarters to the value of the dimes for a total of $2.85. The equation 0.25Q plus 0.10D equals 2.85. The second idea expresses the total number of coins, 18, by simply adding the quantity of the coins. The equation Q plus D equals 18. Choice H shows this system of equations.